Hi, in this video I'm going to walk through how to create a waffle type structure in Grasshopper. Um, as you can see on the left here, this is a uh, structure made up of three parts in each direction, the X and the Z. If I toggle on the original solid that leads to creating this object, you can see it in red here. I'll toggle off the resulting curves and surfaces here to see what it begins as. So this is what we start with, and then this is sort of a version of what we end up with on the left side here, where this object consists of multiple pieces that can be laid out for laser cutting or other forms of CNC manufacturing, such as CNC routing and CNC milling. So in this definition, I'm going to go ahead and walk through at a high level how it works, and then we'll work through building it from scratch. So things like this are pretty common in the world of laser cutting and design. So it's an efficient way to create objects that are complex, objects that are surfaces, and things like this, large pavilions and structures for common places and sculpture and experiences. So it's a great way to prototype complex forms too. This technique is used a lot in architecture to explore different forms. And in our version here, I'm going to use this to take a solid B-rep, boundary representation here, and turn it into the waffled version. So what we start with, if I show my objects here, I have a couple primitives here, so I'm going to hide most of them for now. And actually, let's see, show, and I'm just going to actually delete some of those. So I have I had a few objects in here. They were referenced in this file, but what I'm going to do is step through this, and then we'll build it from scratch. So I start with an ellipse type shape like this, and then I reference it in Grasshopper. So I'm going to hide that. So after I reference it, the first thing to do is to deconstruct, put a box around it and deconstruct it, and that way I can start to get some measurements of its size. And then I go on to making contours. So contouring is essential for this process. You want to make sure you can specify enough contours that represent the shape in a way that makes sense. So once I have contours, and I can specify any number of contours to do this, once I have contours like that, I can go about creating extrusions that get me to, I'm going to go back and hide this, that get me to the general interlocking piece structure. And then once I have the extrudes, I can go about making sure that each piece will notch with another piece. So if I bake these, we can see what we get in this case. So I have the pieces right here that interface with the horizontal pieces. So these could be laid flat and positioned such that the outlines could be laser cut out or cut on a CNC router. So it's once we get to that point, the rest of this logic is sort of about baking the curves to actually fabricate with. So I have the curves like this that I can lay flat and label and produce on a CNC machine. So we're not going to go as far as flattening the pieces, arranging them, or labeling them in this definition. I'll just work through constructing it to what you see here. So I'm going to go ahead and make a new document. So we'll start fresh. And I might reference back to my file here, but let's start fresh. So the first thing we need is a shape. So I was working with an ellipsoid, so I'll continue to do that. So I just picked ellipsoid from center. So I'm going to go ahead and draw an ellipsoid in the center of my Rhino world here. And go to, let's see, I'll go to the front view. And I want this to be 100 millimeters out. And then, let's see, we can make it about, let's say it's about 50, somewhere around 50. And I'm looking at the bottom of my window here to see what my coordinates are. And so now if I go into, let's say the right view, I can see what it will be, what the depth will be. And this could be wider or taller. I could rotate it, I could angle it. I'll go ahead and put this one about there. So I have sort of a football-like shape, but a little more squished. Maybe an egg, maybe some other kind of shape. So once we have this, type brep, bring our brep in here. So let's define our brep. Okay, so that's coming in, so I can hide this. We'll go ahead and put bifocals in here, so it will label everything for us. And then we want to put a box around this, the box command, so it's sort of like a bounding box. If you type box, it'll put anything that goes into the box will show up inside of there, and the box will contain it. Then we want to deconstruct the brep. So we're going to use this to get some lengths, some dimensions of our box. So if I put this into here, then the output will be our trimmed faces, edges, and vertices of the box right here. So I'm going to go ahead and hide my brep for a minute. And I could, if I hook this up, I could get essentially another, the same thing, but I'm going to use the box component. And let's see here, we want to get list item. And so from the list item, we want to go ahead and get the edges. So I'm going to hide this and hide our box, and so we'll see what we get. So with list item, I'm going to select, so I have 12 edges. I'm going to select one of them because I want to get the edge in the X direction and an edge in the Z direction. So let's go ahead and make a second one, and then make a slider and put it in the index. And I'll go ahead and get the leftmost edge here and the bottom edge there. So again, it's the X and the Z directions. And so I can use those along with a number component. And if I hook up the number component, so the output of the list item is a curve, and if I hook up a number component, then I actually get the length of that curve. So I can use it to create a number of segments. So I'm going to hook this up and I'm going to create an integer slider. And so I'm going to go ahead and divide that into 4 pieces. And then I'll go ahead and do the same down here. So essentially these sliders control how many divisions I'll have in each direction. And then next we want to do our contouring. So the first thing we need to do is put our shape, so our B-rep, into the contour because that's what we're contouring. So our, I'll just kind of turn this back on. So our sort of egg-like shape, it's going to go into the contour. And then we need a point to start from. So just like in Rhino, you'd start somewhere. Say I was contouring in the vertical direction, in the Z direction, I would start at the bottom and go to the top. So I need a point, and so I'm going to grab the leftmost point of this curve on the bottom here. And so I can, there's a few ways I could do that. I'll do that by grabbing it from the vertices that are here. So I'll use a list item, and the vertices will go into this list item object, and the 0th vertice, the very first one, shows up right here, so I can just use that. So that will go into my point input, and then the direction, I want to move in the unit X direction. So I'll go ahead and hook the unit X vector up to that, and then the distance will connect up to my divisions here. So by hooking up the distance, this is saying how much space I want between each contour. So the contours I get right there show up. So if I bake those, then we can see I have some curves that represent that. So if I want more contours, I just increase the number of divisions, like so. I'll keep it simple for now. Leave it at 4. So it's 1, 2, 3, 4 divisions. So which is three contours basically. And let's see here. So what I could do too is adjust for. There's a little bit of a kind of strange things that happen with B-reps and the box, sometimes small artifacts. And so to account for this, sometimes it happens, it might be happening here. It has to do with when an object is intersecting with another one. So one way to account for that is to insert an expression under the distance, meaning in here the input is x, the variable x. It's sort of arbitrary, but I can say something like x minus 0.01, something like that, and then I'm ensuring that I won't have any issues on the output. So let's go ahead and we'll copy and paste this contour and do the same thing, but in the unit Z direction. So hook that up instead of in the X. And you can see the contours are starting to happen over here. But we also need to adjust that. So we have 4 and 4. So this one is for the X direction, this one is for the Z direction. So if I were to bake those out, you can see what we get. So I kind of get that. And let's see here. So you can see there's sort of a small contour right there that showed up, and probably a tiny one on the top right here. So those aren't really necessary, so we can account for that later. Let me try to do this actually. Let's delete our offset here and see if we still get that. So that's setting an expression there is really, it just kind of depends on the results of the contouring. So sometimes it affects these little artifacts that might show up. Sometimes it doesn't. It just depends on the number of divisions, really. So if I set this to, let's set this to 8 and set this to 8 and see what happens. So we'll have more divisions. Let's bake those and look at it. So in this case, I don't end up with as many contours, but again, it depends on the B-rep, it depends on the number of divisions, and it depends on if something is intersecting with the box a little bit. So that's good, so I'll go ahead and delete that. So if I run into issues, I'll set those back. So the output of these contours, the contour command, is tree, data tree, and so I'm going to go ahead and flatten that to just make a single list. And let's see, there we go. Oh, we can see we have an elliptical curve. Okay, elliptical curve, yep. So the reason I'm doing that is then I can get the list length, because I want to get the length of each of these lists using the list length command. So I get 7 there, and I will get 7 here too, I believe. So it's one less. And then with these curves, what we can do next is just drop these into some curve objects. Oh, let's see here. Oh, so that's a number. That's right. So we actually want just the curves that are coming out. So go ahead and do that. And let's see, I'm going to turn the list length off for the moment. We might not need that. So, whoops. Go ahead and hide the flattened tree and hide these contours. We're essentially just bringing a version of the contours out over here into these curve objects for convenience. I'm going to go ahead and hide all of this. I'm going to hide the box. And that's good. I'm going to go ahead and save this too. Desktop, I'll call it Waffle Video. Okay, so we have these contours, and I'm actually going to go back down to like 4, just to keep it simple. And our list length is 3 and 3, okay. So that's fine. Okay, so the next thing we need to do is now let's give these things some thickness. So we can do that with the move command and do in the unit x direction. So with this, I'm going to hook up our geometry and give it a vector, unit vector, which we can scale. So we're in millimeters, so I'm going to specify a thickness of 3 millimeters by just putting in 3. And so we can see in our preview here, we're essentially, we have our primary curve and we're creating a secondary curve off of that. And so what we want to do, we're treating this curve as our middle. So what we actually want to do is, instead of offsetting fully by 3, we want to offset by half of that. So to do that, we could just put half in, or we could actually enter an expression right here at the beginning of the unit vector. So we could say x divided by 2. And we could even do, let's see, minus x divided by 2. And that'll go the other to the other side. And then can make a surface. So we'll make a surface off of the offset. So what that will look like now is if I go and turn off my brep here, we'll see that we now have a surface showing up on the offset curve. This is the middle curve, this is the offset curve. And so now we're going to offset or create an extrusion from this surface to 3 millimeters away from it. So extrude, and we give it an input of that surface. So I'm going to hide the move and show the surface, and then we need a direction. So the direction is going to be the unit X direction. And again, we're going to connect up our distance that we want to move, which is 3 millimeters. So we're using this one to offset to the left in the minus direction by half, and then we're using this one to offset to the right fully 3 millimeters. And so I can hide this surface. So now we have an extrusion. So if I were to bake this, we can see we have the beginning of the pieces at the correct thickness that we would need. And so this is, I'm able to visualize that this way. So for the Z direction, we basically just duplicate this and do the same thing, but for the Z. So I'll take this curve into here and replace the unit X with unit Z's. And do the same thing for the expression here, minus X divided by 2. And switch this to there, and switch that to there. And then unit X, or unit Z. Switch that to there, and switch that to there. And so now we get the same result, just in the Z direction. So these are our two B-reps, or two sets of B-reps based around these curves. So I'm going to hide those curves. So this is what we're next going to find the intersection with. So these objects are intersecting with the horizontal pieces. They're actually all intersecting with each other in 3 places right now. And so what we need to do is find those locations using these as inputs. So the way we do that is to use a component called cross-reference. And so the cross-reference component will essentially take in 2 lists and relate every object in each list to every other object in the other list. So if I bring in these 2 lists of items, I have 3 B-reps, 3 B-reps, and so what I get on the output is basically 2 lists that are the same. So next what we want to do is use that, let me see here, to where's the intersect. So what we want to do is we want to use the B-rep to B-rep component, which essentially solves for the intersections of the objects. So if I hook up these 2, then I will get where the objects intersect. So both lists of objects will intersect in these same places, and it'll actually give me as an output, it'll give me all the curves where they intersect. And so if I hide the extrusions now and just look at the intersections, we can see there's actually a lot of sort of artifacts, and they're messy, and so we don't really want that. But what we want is the general shape of the entire intersection. And so that's where we can use a command component called bounding box. And we don't want it to be per object, we want it to be a union box, so it will actually cover every single piece of the set of curves that are together. And so the curves are organized in the data tree here, 2 per branch, it looks like. And that has to do with, for example, this curve and this curve next to it. They're part of the intersection, but they're not connected, but they make up the entire volume of the intersection. So what we want to do is just hook up this to here and make sure this is on union box. If it's not, then you start to get multiple planes being put into a bounding box. So if we just turn on union box, then it makes one large bounding box around all the artifacts. And so if I hide that, now we have some nice bounding boxes for the intersections themselves. So after that, what we want to do next is take these and offset them in each direction to perform essentially a Boolean difference. So if I turn on my extrudes, we can see again kind of where we're at. So I can see inside here and there and there and there. The box that makes up the intersection doesn't quite go to the end here, but that doesn't really matter because we're just going to offset in each direction in the Y direction. So the direction we want to create little slots in. So what we need to do is take these boxes now and deconstruct them. Deconstruct brep. So these are just breps. So we can hook these into here, and we're going to deconstruct them into their faces and edges and vertices. And so I'll hide that, and I'm going to hide these actually. So hide those, and so we have our boxes now deconstructed. And we need to get the length. Via list item. So from the list item, what we need to do is get an edge. We need to get the longest edge of each box. So if we go like this and hook it into a list item, then we can pick the longest edge. So it looks like by default the 0th edge is the short one. So we actually need to find a longer one. So if I hook up 1, let's see if that gives us a longer one. Yes, it does. So we want the length of each box in the Y direction to show up. So just by picking the first item from each list of edges in the tree, we get all of the edges. So let's turn this. Let's get the length of each edge by going into a number, and we have our numbers. If we hook a panel up, we can see what the numbers actually are. Doesn't quite matter right now. So we can see those are our numbers in our data trees. So that's good. And so essentially we're doing kind of what we did before. We're now needing to get the halfway point here, and we're going to shift our boxes by half in each direction, in the Y direction, positive or negative Y, to do a Boolean difference. So let's see, we need our move. We need a move, and we also need to take this number and divide. So division. So we're going to take our length of each edge, and we're going to divide by 2. So we're going to divide it in half. And so if I flatten this, we can actually see. So those are our results. So unflatten, okay. And so now we want to actually shift in the Y direction. So we need a vector. So unit Y. So we'll hook this into here, and then now we have a Y vector, which we can shift with. And so we want to shift. Let's shift first. So shift in the positive direction. By just hooking it up, we'll be shifting in the positive direction. But the input, we need our geometry input. So let's see, we need our extrusion, I believe, right? Yeah, so we need to grab, let's turn our extrusion on. And actually, no, we need our boxes. So boxes. So right here, we'll shift our box over. So we can shift in one direction. And then let's make a copy. And we're still going to use our unit vector, but we need to shift in the other direction now. So our motion itself, we can, let's say x, or we could say like minus x, I think. Yeah, so it's just going to go in the opposite direction. So we have that and that, which we're going to use to subtract or Boolean from our extruded shapes. So the next piece is to use solid difference components. So solid difference, and what solid difference is going to do is perform the operation. Let me hide this one, of cutting away from the extrusion. So I'll bring this extrusion over here. So B rep A is coming from these pieces, and then the geometry going into B is like that. Oh, it looks like what I need to do actually is flatten both of these going in as well. So I have B reps and B reps. So I should have 3 coming out, and I'm putting 9 in there. So let's hide this, and I'll hide my extrusion, and we can see now what's going on. So the B reps that I shifted, or the bounding boxes that I shifted by half, are now being used to carve away from my vertical pieces here. And so if I just do the same thing with the other component here, so this goes into here, and coming out of here goes into there. Now I have the horizontal pieces in the Z direction though. I have these pieces now, toggle these off. So we should get, we get that kind of result. And I have some curves on here somewhere. Let's turn those off. So those are the horizontal pieces, and these are the vertical pieces. So if I were to bake those out, bake like so, I could technically be done there, because I could rotate these like so and lay them out and perform a dupe border, or project the curves down to the C plane, the construction plane. But we'll go ahead and just get the curves out of these extrusions that we would need to laser cut with. So these are sort of the results. That's like the resulting B reps. So let's kind of put them in a box. And so to get the final curves, I'm going to go ahead and hide that. To get the final curves of each piece, what I would have to do here is deconstruct. Again, deconstruct now these B reps. So we'll start with this one. So we're going to deconstruct this into its components. And so we have faces, edges, vertices. So if I hide this, then we can see, right? So we see all the points and the edges and the faces here. And so there's kind of a trick here to getting the larger face from each one of these. And what we could do is just look at the area of all the faces and sort out which one is the largest, because we know the largest face is going to have the biggest contour to lay flat and cut from. So what we could do is get the area. Let's see, get the area of all the faces, and from the area we want to, let's see, sort the list that we get. And so we have areas for the different parts of each one of these pieces, and so we're going to put it into the sort list. And so the sort list will basically go through and rearrange the list by area size. So we'll put the faces into the values, we'll put the keys into, or the area into the keys, and it will reorder the list for me by size. And so now my largest, so if I did a list item, I can look at what the output is. So let's hide these things. So item 0 is apparently nothing, or it's really small. But if I look at, say, item 1, let's see what we get. Or 2, 3. Let's see here. Faces. Oh, I'm looking at the wrong output. So I actually want the values, not the keys. So if I go down to 1, you can see it goes from smaller to larger pieces. So what I'm looking for is probably the very last. It's the very last object in the list that I get, because it's the one with the largest area. So what I can do is, let's disconnect this. So knowing this, the organization of our list now, what I can do is reverse it. Reverse list. I can go in here and reverse it, and that just flips the entire list. So the last item becomes the first item in each branch. So now if I hook this up and I go to item 0, it should be the largest one. So let's say go to 0. There we go. So the 0th item, which by default list item is has an index of 0, so I can just hook that up and I get the last item, which is the largest area. So that's how I can, it's kind of a trick, that's how I can get the largest piece out of a list. And so now, if I go and connect up a curve object and hide this, then I get my final curves. So this can be done for the other side, so this, and I now have my final curves. So I can take, save that, I can take these curves now and bake them. Just go ahead and actually go like this, bake them to my current layer. And so now I can bring them over here and go like so, like that. And you can see they're actually not all in the flat XY plane, but if I wanted to fix that sort of a manual way, I could go here and in my top view I could type project to C plane, project to C plane, and I could delete the input, yes. And what that'll do is if I go to perspective, you can see it then projects them down onto the flat ground the XY plane. So, and then I could do the same thing with these curves. I'll just bring them over here and go to perspective, rotate by 90, and just kind of drag these out in a way that makes sense to project from. So again, they're not flat on the ground plane yet, but if I go to my top view and type project to C plane, delete inputs, yes, perspective, now I can see everything is flat on the ground. So what I could do with these now is I could organize them in a way that makes it a little bit easier to export. So maybe just kind of set them like this. And this is such a simple version of this model, I don't really need to worry about labels, but if I had many more pieces, perhaps tens or hundreds of pieces, depending on the scale of the object or the thickness of material, I would definitely want to follow up this definition right here, continuing it from these curves onto adding in a way to label parts and arrange them on the ground plane so I could easily export them to then laser cut. So with that, the definition is done, and one could go back here to the beginning, save it, and replace this brep with a different object. So let me demonstrate that, and then let's toggle. Okay, so we have our curves there. So let's go back here and put in a different object. So say we have a sphere, and we have it starting there, and it's about that big. Go over here and put a brep in and assign it. Set one brep, okay, and hide this. Okay, and so now if we hook up this to this other object, then now we instantly have our, and I'll hide my sphere now, we have our other curves for the sphere showing up. And again, this only has 4 divisions. If I start to increase this, let's say 8, okay, and it works a little bit harder, then I start to get more divisions. Let's do 8 in this direction too, in the Z direction, and let's see what happens here. So it has to go through and recalculate everything, which is why it takes a second to update. So in Rhino here, I can now see I have lots of divisions. So I'm going to hide those ones and just show these. So that's cool. So I'm going to hide that and show one last kind of visualization technique. So if I have my objects shown like this, and I go to perspective and change it to rendered, I can see them this way. I can see them sort of as ghosted objects. But if I hook up a custom preview to the outputs of these, then I start to see them with materials applied. And so if I hide these now and just see my objects this way, I can start to visualize them in 3D with a kind of materiality. So if I use the swatch, the color swatch on these, then I can assign some different colors and start to just get some different results. For example, I could visualize this way to indicate that I'm going to make this out of two different colors of acrylic, say a black acrylic and a white acrylic together, or go and pick some other color scheme here. Say it's like a blue and a purple or something like that. So it's just a really handy way to visualize the results. Go back to ghosted here, and I guess so. One last way to visualize results. If I bake this out such that we have our bake. Let's see, bake this. Let's see here. Bake each set of objects out right here. So we have 14 poly surfaces now. If I type ZS, okay. So I have these objects, and I'm going to turn off isocurves. So I kind of see just like a cleaner rendered ghosted view. One really handy utility in Rhino is a command called make 2D. So say I really liked this view right here. I could select my object and type make 2D, and it allows me to create line drawings easily. So I can take my view that I'm looking at right now, my perspective view, and I can save out a 2D line drawing version of it. So I could show the lines behind the main outlines, or I can have them hidden. So I'm going to hit apply without the hidden outlines shown, and what it'll do is put it in my top view. So if I go to top now and look over here, I now have a 2D line drawing like this, which I could select these curves and export it as an Illustrator file and sort of compose a 2D and 3D-esque, 3D-esque line drawing version, along with my flat 2D pieces, if I were to save these ones out as 2D production files. So just a couple ways to visualize the results. And with that, the video is done. Good luck.